Look up on a clear winter night, and you might see something that has captivated humanity for thousands of years. A small cluster of stars huddled together, brighter than their neighbors, seeming to form a family in the darkness. What you are witnessing is not an illusion or a trick of perspective. Those stars truly are together, bound by gravity and history, siblings born from the same cosmic cloud. Tonight, we will journey to these stellar families, from the young and scattered to the ancient and impossibly dense. What secrets do these clusters hold about the nature of stars, and what can they teach us about connection itself? Across the vast expanse of our galaxy, stars are not always born alone. In fact, most stars begin their lives as part of a family, emerging together from giant molecular clouds of gas and dust. These stellar nurseries collapse under their own gravity, fragmenting into hundreds or thousands of pockets, each one igniting to become a newborn star. What remains is a star cluster, a group of siblings sharing the same cosmic birthday and drifting through space together. Some of these families are loose and temporary, while others are ancient and eternal. Together, we will explore both kinds and discover what makes each one unique. Think about what it means for stars to be born together. These are not just random neighbors passing in the night. Every star in a cluster formed from the same material at roughly the same moment in cosmic time. They share a chemical composition, an age, and a history that stretches back millions or even billions of years. When astronomers study a star cluster, they are looking at a laboratory where every variable except the mass of individual stars is held constant. This makes clusters invaluable for understanding how stars of different sizes evolve and age. But beyond science, there is something deeply moving about these cosmic families. Our galaxy contains two distinct types of star clusters, and they could not be more different from one another. The first type, called open clusters, are youthful and sparse. They contain anywhere from a few dozen to a few thousand stars spread across a region of space tens of light years wide. These clusters are found in the flat disk of our galaxy, nestled among the spiral arms where star formation is still active. They are the adolescents of the stellar world, young and energetic but destined to drift apart over time. We will visit them first on our journey tonight. The second type of cluster is something altogether more ancient and magnificent. These are the globular clusters, enormous spheres containing hundreds of thousands or even millions of stars packed into a volume of space only 100 light years across. If you could stand on a planet within a globular cluster, your night sky would be ablaze with thousands of stars brighter than Venus appears from Earth. Globular clusters are relics from the early universe, formed when our galaxy was still young. They orbit the galactic center in a vast halo, moving through space like ancient sentinels watching over the Milky Way's long history. Why do these two types of clusters exist, and why are they so different? The answer lies in when and how they formed. Open clusters are being born even now from fresh clouds of gas enriched with elements created by previous generations of stars. They form in regions where turbulence and stellar winds quickly disperse the leftover material, leaving the newborn stars loosely bound. Globular clusters, on the other hand, formed in the chaotic early universe when gas was denser and more pristine. Their formation was violent and efficient, creating massive, tightly bound systems that have survived for over 10 billion years. Each type tells a different chapter of our galaxy's story. As we prepare to visit these stellar families up close, consider this question: what does it mean for a star to have siblings? Throughout the universe, most stars will spend their entire existence in isolation, never again encountering the brothers and sisters they were born with. But for a time, whether brief or eternal, these stars share space and history. They influence each other through gravity, they illuminate each other's environments, and in the case of the densest clusters, they sometimes even collide and merge. In a universe so vast and empty, star clusters remind us that connection is possible, that families can endure. We will begin our exploration with the open clusters, those young and beautiful congregations that dot the spiral arms of our galaxy. Then, we will venture into the realm of the globular clusters, those ancient treasures that have witnessed nearly the entire history of the cosmos. Along the way, we will discover what it is like to live within these stellar communities, how they are born, how they evolve, and what eventually happens when they drift apart or endure for eternity. Take a deep breath, relax, and let us step together into the light of these cosmic families. Our journey begins now. Open clusters are the epitome of stellar youth and vitality. Unlike their ancient globular cousins, these clusters are often only a few million to a few 100 million years old. In cosmic terms, they are newborns. They form within the spiral arms of galaxies like our Milky Way, where vast clouds of hydrogen gas and dust collapse to create new generations of stars. The process is messy and beautiful, leaving behind not just stars but also remnants of the natal cloud, glowing nebulae that illuminate the young cluster with ethereal light. When we look at an open cluster, we are seeing stellar childhood captured in time. What defines an open cluster is not just its age, but its looseness. These clusters contain anywhere from a few dozen to a few thousand stars, spread across a region typically 20 to 30 light years in diameter. That might sound crowded, but remember that even the nearest star to our Sun is over 4 light years away. In an open cluster, stars are closer neighbors than average, but they are still separated by trillions of kilometers. This loose structure is both a blessing and a curse. It allows us to see individual stars clearly, but it also means the cluster will not hold together forever. The gravity that binds an open cluster is gentle and impermanent. Over tens or hundreds of millions of years, encounters with giant molecular clouds, gravitational tugs from the galaxy itself, and the internal dynamics of the cluster will slowly pull it apart. One by one, stars will drift away, becoming solitary wanderers in the galactic disk. Eventually, the cluster dissolves completely, its stars scattered across the spiral arm where they were born. But while they last, open clusters are magnificent. They are cosmic laboratories and celestial gardens, places where we can study the life cycle of stars in exquisite detail. Our galaxy contains thousands of open clusters, though many are hidden behind dust or lost in the crowded star fields of the Milky Way. The ones we can see with the naked eye have been known since ancient times, woven into myths and legends. Sailors used them for navigation. Poets wrote of their beauty. Astronomers measured their distances in compositions, unlocking secrets about the structure of our galaxy. Each open cluster is unique, with its own population of stars, its own history, and its own destiny. Some are rich and massive blue stars that burn brilliantly but briefly. Others are older, dominated by cooler orange and red stars. Among the most famous open clusters is one you have almost certainly seen. It rises in the autumn and winter sky, a tiny knot of light that looks like a miniature dipper. The ancient Greeks called it the Pleiades, the Seven Sisters, daughters of Atlas condemned to flee across the heavens. Modern telescopes reveal not 7 stars, but hundreds, a jewel box of blue-white stars wrapped in faint nebulosity. The Pleiades is young, only about 100 million years old, and it is close to us, just over 400 light years away. It is the perfect place to begin our exploration of open clusters up close, but the Pleiades is just one example among thousands. Consider the beehive cluster in the constellation Cancer, an older open cluster about 600 million years old, visible to the naked eye as a misty patch. Or the double cluster in Perseus, actually 2 separate clusters that appear side by side in the sky, each one a stunning concentration of young, hot stars. Or the wild and sprawling cluster, NGC 2244, sitting at the center of the Rosette Nebula, its stars actively sculpting the gas around them with powerful stellar winds. Each cluster is a masterpiece, a snapshot of stellar birth and youth captured for us to study and admire. As we prepare to dive deep into one of these clusters, remember that what you are about to see is not a static painting, but a dynamic system. Stars within an open cluster are moving, orbiting each other in a slow gravitational dance. Some are evolving rapidly, swelling into red giants or exploding as supernovae. Others are just reaching the prime of their lives, stable and steady. And all around them, the remnants of their birth nebula may still glow softly, illuminated by the very stars it created. Open clusters are youth and energy made visible. Let us enter one now and see what it is like to stand among newborn stars. Let us approach the Pleiades as if we were traveling in a spacecraft capable of crossing light years in moments. From Earth, the cluster appears as a compact group of stars, but as we draw nearer, the perspective transforms dramatically. What seemed like a handful of stars resolves into dozens, then hundreds. The 7 brightest sisters, Alcyone, Atlas, Electra, Maia, Merope, Tagetha, and Pleione, are revealed to be brilliant blue-white giants, each one many times more massive and luminous than our Sun. But they are just the most prominent members of a family that includes over 1,000 stars. We are entering a stellar city, young and radiant. One of the first things you would notice upon entering the Pleiades is the color. These stars are hot, with surface temperatures reaching 30,000 degrees Celsius or more. They emit most of their light in the blue and ultraviolet part of the spectrum, giving the cluster a distinctly cool, almost electric appearance. This is the signature of massive young stars that are burning through their hydrogen fuel at a furious rate. Unlike our Sun, which will shine steadily for 10 billion years, these giants will live fast and die young, exhausting their fuel in only a few 100 million years. They are cosmic candles burning brightly but briefly. Surrounding these hot stars is something unexpected and beautiful. The Pleiades is passing through an interstellar cloud, and the starlight is scattering off tiny dust grains in the cloud, creating a phenomenon called a reflection nebula. This is not the remnant of the cluster's birth. That material was blown away long ago, but rather a chance encounter with another cloud during the cluster's journey through the galaxy. The result is a delicate blue glow that wraps around the brightest stars like cosmic silk. It is one of the most photographed sights in amateur astronomy, and for good reason. It is breathtakingly beautiful, but the Pleiades is not just about the bright stars. As we fly deeper into the cluster, we begin to see the fainter members of the family. Here are smaller stars, cooler and dimmer, orange and red dwarfs that will outlive their massive siblings by billions of years. There are binary star systems where 2 stars orbit each other closely, locked in gravitational embrace. There are even brown dwarfs, objects too small to sustain, hydrogen fusion, glowing faintly with the heat of their formation. Every star here was born together about 100 million years ago, and they have been drifting through space as a group ever since. They are a true family, bound by common origin. Imagine living on a planet within the Pleiades. Your night sky would be unlike anything we experience on Earth. Instead of a few thousand visible stars, you would see tens of thousands, the combined light of the cluster's members creating a soft glow across the heavens. The brightest stars would cast shadows, and there would be no true darkness, only a perpetual twilight illuminated by your stellar siblings. Daytime would be bright and blue-white, your Sun, one of those hot, massive stars. But such a planet would have a limited future. In a few 100 million years, your star will swell into a red giant, engulfing any inner planets before shedding its outer layers and fading away. The Pleiades cluster itself will not last forever. Already, after only 100 million years, the cluster is beginning to spread out. The gravitational attraction between its member stars is weak, and encounters with giant molecular clouds in the galactic disk are gradually pulling stars away. In another few 100 million years, the cluster will be completely dispersed, its stars scattered across hundreds of light years. Future astronomers will still be able to identify them by their common motion and chemical composition, recognizing them as siblings even though they are separated by vast distances. The family will endure in memory, if not in proximity. Before we leave the Pleiades, take one last look around. You are floating in a region of space that has been sacred to countless cultures throughout human history. Japanese tradition calls this cluster Subaru. Hindu mythology knows it as Kritika. Australian Aboriginal stories tell of 7 women who fled to the sky. Every human civilization has looked up and seen these stars, and everyone has woven them into their understanding of the cosmos. The Pleiades is more than a star cluster. It is a cultural touchstone, a reminder that we all share the same sky, the same universe, the same sense of wonder when we look up into the night. To truly understand open clusters, we must go back to the beginning, to the moment before stars exist. Imagine a vast cloud of gas floating in the spiral arm of a galaxy, hundreds of light years across, composed mostly of hydrogen with traces of helium and heavier elements. This cloud is cold, only about 10 degrees above absolute zero, and incredibly diffuse. For millions of years, it drifts through space, seemingly eternal and unchanging. But within this cloud, something is about to happen. A nearby supernova explodes, or a collision with another cloud occurs, and suddenly the delicate balance is disrupted. Gravity begins to win. As the cloud begins to collapse, it does not do so uniformly. Turbulence and rotation cause it to fragment into smaller clumps, each one collapsing independently. These clumps become denser and hotter as gravity pulls material inward. Within the densest cores, temperatures and pressures climb until a critical threshold is reached. Suddenly, nuclear fusion ignites. Hydrogen atoms begin fusing into helium, releasing tremendous amounts of energy. Spawn, not just one star, but hundreds or thousands, all igniting within a relatively short span of cosmic time. This is the birth of an open cluster, a generation of stars emerging together from a single cloud. The first stars to form are often the most massive, and they have an immediate and dramatic impact on their surroundings. These massive stars emit intense ultraviolet radiation and powerful stellar winds that begin to disperse the remaining gas in the cloud. The result is spectacular. Glowing nebulae form around the young stars, ionized by their radiation and sculpted into pillars and bubbles by their winds. This is the stage where many famous star-forming regions exist. Places like the Eagle Nebula with its iconic pillars of creation, or the Orion Nebula, where we can watch star formation happening in real time. Open clusters are born in fire and light. Within a few million years, the most massive stars have blown away most of the natal gas, leaving behind a revealed cluster of newborn stars. But not all stars are created equal in these clusters. The most massive stars, 10 or 20 times the mass of the Sun, are brilliant and blue, dominating the visual appearance of the cluster. But they are also rare. The vast majority of stars in the cluster are much smaller, red and orange dwarfs that will live for trillions of years. There are also intermediate mass stars like our Sun, steady and reliable. Together, these stars form a community, each member contributing to the cluster's overall character and evolution. The stars in a young, open cluster are not standing still. They are orbiting each other in a complex gravitational dance, their paths determined by the cluster's overall mass distribution. Some stars orbit near the center where the density is highest. Others inhabit the outskirts, moving more slowly and feeling less gravitational pull. Occasionally, stars pass close to each other, their orbits deflected by the encounter. In rare cases, 2 stars might even collide or be ejected from the cluster entirely, flung out into space at high velocity. The cluster is a dynamic system, constantly evolving as its members interact with each other and with the galaxy around them. Over time, the cluster begins to age and change. The most massive stars, those brilliant blue giants that once dominated, evolve rapidly. Within just a few million years, they exhaust their hydrogen fuel and swell into supergiants before exploding as supernovae. These explosions can actually help unbind the cluster, injecting energy and momentum that push stars apart. Meanwhile, the smaller stars are barely changed, still on the main sequence where they will remain for billions of years. An open cluster is like a snapshot of stellar evolution, showing us stars at different stages of life, all with the same birthday but very different destinies. As we watch the cluster continue to evolve over hundreds of millions of years, we see it gradually dissolve. Stars that were once neighbors drift apart, carried by their individual orbits through the galaxy. Some are ejected by close encounters with other stars. Some are pulled away by the tidal forces of the Milky Way itself. Eventually, only the faintest stars remain bound together, and even they will disperse given enough time. An open cluster is a temporary gathering, beautiful and instructive, but not eternal. Yet the stars remember their common origin, carrying with them identical chemical compositions that mark them as siblings, even when separated by vast distances. Family endures in memory and in matter. What would it be like to live in a planetary system within an open cluster? Consider a planet orbiting a sun-like star in the heart of a young cluster, perhaps similar to the Pleiades. Your star would be surrounded by hundreds of stellar siblings, some of them visible to the naked eye in your daytime sky, many more scattered across the night. The nearest stars might be only a light year away, close enough that if they harbored civilizations, communication would be possible over the span of a few years. This is a very different environment from the isolation we experience here on Earth, where our nearest stellar neighbor is over 4 light-years distant. The increased stellar density in an open cluster has profound implications. First, the night sky would be spectacular beyond imagination. Instead of the few thousand stars visible from a dark site on Earth, you might see tens of thousands of stars, creating a continuous glow across the heavens. The Milky Way would still be visible, but it would be overwhelmed by the local cluster members. Meteor showers might be more common, as the cluster's collective gravity could perturb distant comets and asteroids into planet-crossing orbits. There would be a constant, gentle light from your stellar siblings, a perpetual twilight even on the darkest nights. It would be beautiful, but also alien. But living in an open cluster would also pose challenges. The most massive stars in the cluster, those brilliant blue giants, are ticking time bombs. Within a few million to a few tens of millions of years, they will explode as supernovae, releasing bursts of radiation and high-energy particles that could sterilize nearby planets. If your world is within a few dozen light-years of such an explosion, the ozone layer could be stripped away, allowing deadly ultraviolet radiation to reach the surface. Life might need to retreat underground or underwater, waiting for the danger to pass. The cluster is beautiful, but it is also dangerous, at least in its youth. Another consequence of the higher stellar density is an increased chance of close stellar encounters. Every few million years, a star might pass within a light year of your home system, temporarily perturbing the orbits of comets in the outer solar system and potentially sending some of them careening toward the inner planets. These encounters would be slow and stately by human standards, taking thousands of years to unfold, but they could trigger episodes of increased impacts on planetary surfaces. On the other hand, such close passages might also facilitate the exchange of material between star systems. A comet ejected from one system could be captured by another, potentially even carrying microbes between worlds. Panspermia could be more common in open clusters. For a hypothetical civilization within an open cluster, the abundance of nearby stars could be both a blessing and a curse. Interstellar travel would be more feasible, with potential colony worlds only a few light years away instead of 4 or more. A sufficiently advanced civilization might establish an interstellar empire within the cluster, colonizing dozens or even hundreds of star systems. Communication between colonies would be slow but manageable, with round-trip messages taking only a few years. The cluster could become a single vast community, a stellar federation bound not just by gravity, but by culture and communication. But any civilization within an open cluster would have to contend with the cluster's eventual dissolution. Over hundreds of millions of years, the gravitational bonds holding the cluster together would weaken. Star systems would begin to drift apart, the distances between neighbors growing from light years to tens or hundreds of light years. The empire would fragment, the colonies becoming isolated as the journey times between stars grew prohibitively long. Eventually, the cluster's stars would be scattered across the galactic disk, recognizable as siblings only by their shared chemistry and common motion. The family would be broken not by choice but by the inexorable dynamics of galactic evolution. Despite the challenges, there is something profoundly appealing about the idea of living in an open cluster. It represents the possibility of cosmic community, of being part of something larger than a single isolated world. For a few 100 million years, the cluster's stars would be true neighbors, sharing space and light. They would illuminate each other's skies and influence each other's evolution. And even after the cluster dispersed, those stars would carry the memory of their shared origin, marked forever by their common chemistry. In the vastness of the galaxy, that shared history would be a connection, a reminder that even in the cosmic dark, families can exist. Now we turn our attention to a very different kind of stellar family. Globular clusters are among the most ancient structures in the universe, relics from the earliest epochs of galaxy formation. Where open clusters are young, loose, and temporary, globular clusters are old, tightly bound, and seemingly eternal. They contain hundreds of thousands to millions of stars packed into a spherical region only about 100 light-years across. If you could shrink an open cluster down to the size of a city, a globular cluster would be the size of a continent, dense and sprawling. These are the elders of the galaxy, and they have stories to tell that stretch back nearly to the beginning of time itself. Globular clusters orbit the Milky Way in a vast halo, a roughly spherical distribution that surrounds the flat galactic disk. There are about 150 known globular clusters in our galaxy, each one following a highly elliptical orbit that takes it from the outer halo down through the galactic plane and back out again. These orbits can take hundreds of millions of years to complete, and during their journey, the clusters remain remarkably stable, held together by their immense combined gravity. They are survivors, having weathered nearly the entire history of our galaxy without dissolving, a testament to their incredible binding energy and the perfect balance between their internal gravity and external tidal forces. The stars within globular clusters are ancient, typically 10 to 13 billion years old. This makes them some of the oldest stars in the universe, born when the cosmos was less than 1 billion years old. In fact, by measuring the ages of globular cluster stars, astronomers can place lower limits on the age of the universe itself. No star in a globular cluster can be younger than about 10 billion years, which tells us the universe must be at least that old. These clusters are cosmic fossils, preserving conditions and compositions from the early universe, offering us a window into a time when galaxies were just beginning to form. What is it about globular clusters that allows them to survive for so long? The answer is density and mass. A typical globular cluster contains as much mass as several 100,000 suns, all packed into a relatively small volume. The resulting gravity is strong enough to hold the cluster together despite the tidal forces exerted by the galaxy as the cluster orbits through it. In the core of a globular cluster, stars can be separated by distances of only a few light weeks, 1,000 times closer than the nearest star to our Sun. This extreme density creates a unique environment where stellar interactions are common and the cluster behaves almost like a single vast gravitational entity. The stars in globular clusters are chemically distinct from younger stars in the galactic disk. They contain very few heavy elements, what astronomers call metals, because they formed before many generations of supernovae had enriched the interstellar medium with carbon, oxygen, iron, and other elements. This metal-poor composition gives the stars a characteristic color, typically a warm golden or orange-yellow rather than the blue-white of young massive stars. The most massive stars that once existed in globular clusters have long since died, leaving behind only low and intermediate mass stars, white dwarfs, neutron stars, and black holes. These clusters are cities of the old and the patient. Among the most famous globular clusters is Omega Centauri, the largest and most massive globular in our galaxy. It contains over 10 million stars and is visible to the naked eye from the southern hemisphere, appearing as a diffuse patch of light about as wide as the full moon. Some astronomers believe Omega Centauri is not actually a true globular cluster, but rather the remnant core of a small galaxy that was cannibalized by the Milky Way billions of years ago. If so, it is a survivor of an ancient cataclysm, the last fragment of a world that no longer exists. Either way, it is a spectacular sight through any telescope, a perfect sphere of stars that seems to glow from within. Another magnificent example is M13, the Great Globular Cluster in Hercules, one of the finest such clusters visible from northern latitudes. Even through binoculars, M13 is impressive, a misty ball of light that resolves into individual stars through a telescope. It contains about 300,000 stars and lies 25,000 light-years away. In 1974, astronomers used the Arecibo radio telescope to transmit a message toward M13, a symbolic gesture known as the Arecibo message. If any civilization orbits one of those stars, they will receive our greeting in about 25,000 years, and we might hear a reply 50,000 years from now. It is a reminder that these clusters are not just abstract objects, but potential homes for life and intelligence. Let us journey now into the heart of Omega Centauri, the grandest of all globular clusters in our galaxy. From Earth, it appears as a fuzzy star, but as we approach, it grows and transforms into something almost incomprehensible. A vast sphere of light, 10 million stars bound together by gravity, spanning over 200 light-years from edge to edge. Even from a distance of thousands of light-years, the cluster dominates the view, a concentrated blaze of golden light floating in the darkness. This is not just a cluster of stars. It is a world unto itself, a miniature galaxy with its own dynamics, its own history, and possibly its own secrets. As we cross into the outer regions of Omega Centauri, the stellar density begins to increase noticeably. Where the space between stars in our neighborhood is measured in light-years, here it shrinks to mere light months. Stars that would be invisible from Earth are now bright enough to cast faint shadows. The combined light of millions of distant cluster members creates a soft, ever-present glow, like a perpetual dawn. Looking back toward the Milky Way, our home galaxy appears as a distant band of light, unremarkable compared to the brilliance of the cluster itself. We have entered a different realm, a place where stars are the rule, not the exception. The stars we pass on our journey inward are ancient, their age is measured in billions of years. These are low-mass stars, orange and red dwarfs that burn their hydrogen fuel slowly and steadily. Mixed among them are red giants, stars that have exhausted the hydrogen in their cores and swollen to enormous sizes. These giants are in their final stages of life, shedding their outer layers into space and creating beautiful planetary nebulae that briefly illuminate the surrounding region before fading. There are also white dwarfs, the dense remnants of dead stars no larger than Earth but containing the mass of the Sun. Every star here is old, a survivor from the early universe. As we continue inward, the stellar density increases dramatically. Stars that were separated by light months are now only light weeks apart. The sky is ablaze with thousands of stars bright enough to read by, and the combined light is intense, almost overwhelming. This is the intermediate region of the cluster, where stellar interactions begin to dominate the dynamics. Close encounters between stars are common here, occurring every few million years for any given star. These encounters can alter orbits, strip away outer layers of evolved stars, and occasionally result in stellar collisions or captures. The cluster is not static, but a dynamic, evolving system where stars constantly interact. Finally, we approach the core of Omega Centauri. The density here is almost unimaginable, with stars separated by only a few light days or even light hours. This is as close as stars can get without merging, and indeed, mergers are thought to be common in globular cluster cores. The result is exotic, stellar objects, blue stragglers that appear younger than they should, massive white dwarfs formed from the merger of two smaller ones, and even black holes lurking unseen in the depths. The core is bright, so bright that if you could stand on a planet here, the combined light of all the surrounding stars would be as bright as twilight on Earth, 24 hours a day. At the very center of Omega Centauri, there may be an even more exotic object. Some astronomers believe there is an intermediate mass black hole lurking in the core, containing tens of thousands of solar masses. Such black holes are rare and poorly understood, bridging the gap between stellar mass black holes formed from supernovae and supermassive black holes found in galactic centers. The evidence is indirect, based on the motions of stars near the core, but if the black hole exists, it is a relic from the cluster's formation, possibly the central black hole of the small galaxy that Omega Centauri once was before being absorbed by the Milky Way. As we pause at the heart of Omega Centauri, surrounded by millions of ancient stars, consider what we are witnessing. This cluster has existed for over 12 billion years, formed when the universe was still in its infancy. It has survived countless close passages through the Milky Way's disk, each one stripping away some of its outer stars but leaving the core intact. It has witnessed the birth and death of generations of stars, the formation of planets, and possibly even the rise and fall of civilizations. It is a monument to gravity's power and time's patience. And it is just one of many such clusters, each with its own history and mysteries. We are standing in a cathedral of stars, ancient and enduring. Globular clusters are more than just beautiful. They are time capsules, preserving conditions from the early universe and allowing us to test our theories of stellar evolution, galaxy formation, and even cosmology itself. When astronomers study globular clusters, they are looking back in time, seeing stars that formed when the universe was less than 1 billion years old, when galaxies were still assembling from smaller fragments, and when the first generations of stars were enriching the cosmos with heavy elements. The information encoded in globular clusters is invaluable, making them some of the most studied objects in astronomy despite their age and distance. One of the most important uses of globular clusters is in measuring the age of the universe. By studying the colors and brightnesses of stars on what is called the main sequence turnoff, the point where stars begin to evolve away from stable hydrogen burning, astronomers can determine the age of the cluster's stellar population. The oldest globular clusters in our galaxy are about 12 to 13 billion years old, which means the universe itself must be at least that old. Combined with other measurements, such as the cosmic microwave background radiation, this gives us a consistent age for the universe of about 13.8 billion years. Globular clusters are cosmic clocks. The chemical composition of stars in globular clusters tells another fascinating story. These stars are metal poor, containing only a tiny fraction of the heavy elements found in younger stars like the Sun. This makes sense because they formed before many generations of supernovae had seeded the interstellar medium with carbon, oxygen, nitrogen, and iron. By measuring the metallicity of globular cluster stars, astronomers can trace the chemical evolution of the galaxy, understanding how the abundance of heavy elements has increased over time. Each generation of stars creates more heavy elements through nuclear fusion, and those elements are returned to space when stars die, enriching the gas that forms new stars. But not all globular clusters are identical. Recent studies have revealed that many clusters contain multiple populations of stars with slightly different chemical compositions. Some stars are enriched in elements like sodium and aluminum, while others are not. The leading theory is that the first generation of stars in the cluster produced these elements and shed them into the cluster's environment, where they were incorporated into a second generation of stars. This suggests that globular cluster formation was not a single, instantaneous event, but rather a process that unfolded over tens of millions of years. The clusters we see today are the survivors of this complex formation process. Globular clusters also serve as laboratories for testing theories of stellar dynamics. Because the clusters are so dense, three-body interactions are common, where two stars pass close to a third, resulting in one star being ejected at high velocity. Over billions of years, this process can strip stars from the cluster, creating tidal tails that extend along the cluster's orbit. Astronomers have detected these tails around several globular clusters, proving that even these ancient, stable systems are slowly evaporating. Eventually, in tens of billions of years, even the most massive globular clusters will dissolve completely, their stars scattered across the galactic halo. Perhaps the most intriguing question about globular clusters is where they came from. Did they form within the Milky Way, or were some of them captured from smaller galaxies that our galaxy cannibalized? The evidence suggests both. Some globular clusters have orbits and compositions consistent with formation in the Milky Way's halo. Others, like Omega Centauri, show signs of having been the cause of dwarf galaxies that were torn apart by tidal forces. Still others may have formed in clusters of galaxies and then been ejected into intergalactic space, only to be captured later by the Milky Way. Globular clusters are not just inhabitants of our galaxy, but also its history book. As we contemplate these ancient stellar cities, we are confronted with a profound realization. Globular clusters have been around for most of the universe's history. They have witnessed the formation of galaxies, the birth and death of countless stars, and the gradual enrichment of the cosmos with heavy elements. They are survivors, having endured for longer than almost any other structure we can observe. And yet, they are not eternal. Even globular clusters will eventually dissolve, their stars scattered to the winds of time. But for now, they endure. One of the most striking differences between globular clusters and open clusters is the sheer density of stars in the globular cluster core. We have touched on this already, but let us explore it in greater depth. In the core of a massive globular cluster like Omega Centauri or 47 Tucanae, stars can be separated by distances of only a few light days or light weeks. To put this in perspective, if our sun were in such a core, the nearest stars would be closer to us than the outer edge of our Kuiper belt, the region where Pluto and other dwarf planets orbit. The night sky would be unimaginably brilliant, a dome of thousands of stars, each one bright enough to cast shadows. This extreme density has profound implications for the stars themselves. In such an environment, close encounters between stars are not rare events but regular occurrences. Every few million years, a star might pass within a light week or less of another star. These encounters can exchange energy and momentum, altering orbits and occasionally ejecting stars from the cluster entirely. In some cases, two stars might pass so close that they interact gravitationally in complex ways, forming temporary binary systems or even colliding directly. The globular cluster core is a dynamic, chaotic place where stellar interactions dominate the evolution of the system. One of the most fascinating consequences of this density is the phenomenon of core collapse. Over billions of years, energy is slowly transferred from the inner regions of a globular cluster to the outer regions through stellar encounters. The core loses energy and contracts, becoming denser and hotter while the outer regions expand. This process continues until the core becomes so dense that it can support itself through a different mechanism, possibly involving the formation of a central black hole or a population of tightly bound binary stars. About 20% of globular clusters are in a state of core collapse, their centers extraordinarily dense and bright, regions of intense stellar activity. The high stellar density in globular cluster cores also leads to the formation of exotic stellar objects. One such object is the blue straggler, a star that appears younger and more massive than it should be given the age of the cluster. These stars are thought to form either through the collision and merger of two stars or through mass transfer in a close binary system. The result is a star that appears out of place, bright and blue in a cluster where all the massive stars should have died billions of years ago. Blue stragglers are like cosmic anomalies, their existence revealing the violent and dynamic nature of globular cluster cores. Another exotic product of the crowded core environment is the millisecond pulsar, a rapidly spinning neutron star that emits beams of radio waves as it rotates. Millisecond pulsars are thought to form when a neutron star in a binary system accretes material from its companion, spinning up to enormous speeds. Globular clusters are rich in millisecond pulsars, with some clusters containing dozens of these objects. They are cosmic lighthouses, their pulses arriving with incredible regularity, allowing astronomers to study the extreme physics of neutron stars and to test theories of gravity in strong field regimes. The cluster core is not just crowded, but also a factory for creating extreme objects. Living on a planet within a globular cluster core would be unlike anything we can easily imagine. The constant starlight would mean no true night, only variations in brightness as different stars rose and set. The sky would be a constantly shifting tapestry of stellar colors, yellows and oranges and reds from the ancient stars, with occasional flashes of blue from blue stragglers or young stellar mergers. The gravitational environment would be complex, with the combined pull of thousands of nearby stars creating subtle tides on the planet's surface. And there would be the ever-present risk of a close stellar encounter disrupting the planetary system entirely, ejecting planets into interstellar space. Despite these challenges, or perhaps because of them, the idea of life in a globular cluster core is tantalizing. If civilizations arose there, they would have access to millions of stars within a relatively small volume of space. Interstellar travel would be easier than anywhere else in the galaxy, with neighboring stars only light weeks away. A sufficiently advanced civilization could establish an empire spanning thousands of star systems, all within a region only a few hundred light-years across. Communication between stars would be feasible, and the collective knowledge of such a civilization would be staggering. The globular cluster core could be the ultimate cosmic metropolis, a Dyson sphere at galactic scale. We have now explored both types of star clusters in depth, from the young and scattered open clusters to the ancient and dense globular clusters. Let us now compare them directly, understanding what makes each type unique and what they can teach us about the universe. On the surface, both are groups of stars born together and bound by gravity. But that is where the similarities end. Open clusters and globular clusters are as different from each other as a small village is from a major city, each with its own character, history, and destiny. By comparing them, we gain insight into the full range of ways stars can organize themselves in the cosmos. The most obvious difference is age. Open clusters are young, typically a few million to a few 100 million years old. Globular clusters are ancient, 10 to 13 billion years old, nearly as old as the universe itself. This age difference is reflected in their stellar populations. Open clusters contain massive blue stars that will not live long, along with smaller, longer-lived stars. Globular clusters have lost all their massive stars long ago, leaving only low-mass stars, red giants, and the remnants of dead stars like white dwarfs and neutron stars. An open cluster is a nursery full of youth and energy. Globular cluster is a retirement home populated by the old and the patient. Size and stellar count also differ dramatically. Open clusters contain dozens to thousands of stars spread across tens of light years. Globular clusters contain hundreds of thousands to millions of stars packed into regions only about 100 light years across. The density difference is staggering. In an open cluster, stars are slightly closer neighbors than average, but still well separated. In a globular cluster core, stars are packed so tightly that close encounters are common and the sky is ablaze with starlight. An open cluster is spacious and sparse. A globular cluster is crowded and intense, especially in its core. Location within the galaxy is another key difference. Open clusters are found in the galactic disk, particularly in the spiral arms where star formation is ongoing. They orbit the galactic center in nearly circular paths along with the rest of the disk material. Globular clusters, on the other hand, are found in the galactic halo, a roughly spherical distribution surrounding the disk. They follow highly elliptical orbits that take them far above and below the galactic plane. This difference in location reflects their different origins. Open clusters form from fresh gas in active star-forming regions. Globular clusters formed in the early chaotic universe and have been orbiting the galaxy ever since. Chemical composition also differs significantly. Stars in open clusters are metal-rich, containing similar or even higher abundances of heavy elements compared to the Sun. They formed from gas that had been enriched by previous generations of stars. Stars in globular clusters are metal poor, containing only a small fraction of the heavy elements found in the Sun. They formed from nearly pristine primordial gas before much nucleosynthesis had occurred in the universe. By studying the metallicity of different clusters, astronomers can trace the chemical evolution of the galaxy over billions of years, seeing how each generation of stars has enriched the cosmos with new elements. Perhaps the most poignant difference is longevity and fate. Open clusters are temporary. Over tens to hundreds of millions of years, they will be pulled apart by galactic tides, encounters with molecular clouds, and their own internal dynamics. Their stars will scatter across the galaxy, becoming indistinguishable from field stars except by their shared chemistry and motion. Globular clusters, however, are eternal, or nearly so. They will survive for tens of billions of years, possibly longer than the Milky Way itself if our galaxy eventually merges with Andromeda. They are gravitationally bound so tightly that they can withstand almost anything the universe throws at them. An open cluster is a fleeting gathering. A globular cluster is forever. Despite their differences, both types of clusters are invaluable to astronomy. Open clusters allow us to study stellar evolution in detail because all the stars are the same age and composition, differing only in mass. Globular clusters allow us to study the early universe, stellar dynamics in extreme environments, and the formation history of galaxies. Together, they span the entire range of stellar community types, from loose and temporary to dense and eternal. They are cosmic laboratories, natural experiments that allow us to test our understanding of stars, gravity, and time. And they are beautiful. each in its own way, reminding us of the diversity and wonder of the universe. All things in the universe, even star clusters, have a finite lifespan. We have seen that open clusters are particularly vulnerable, destined to dissolve over relatively short timescales. But even globular clusters are not truly eternal. Over tens of billions of years, they will slowly evaporate, losing stars one by one to the galactic halo. Let us now explore the mechanisms that lead to cluster dissolution and consider what happens to the stars after their family is broken. It is a bittersweet story, one that speaks to both the impermanence of structure and the enduring legacy of shared history. For open clusters, dissolution begins almost immediately after formation. The cluster is born with a certain amount of binding energy, the gravitational energy holding it together. But encounters with giant molecular clouds, the tidal forces of the galaxy, and internal stellar interactions all work to remove that energy. Each encounter strips away a few stars from the cluster's outer regions. Each passage through the galactic disk subjects the cluster to strong tidal forces that can tear it apart. Within a few 100 million years, most open clusters have lost so many stars that they no longer exist as coherent structures. Their stars become part of the general field population. But even after an open cluster has dissolved, its stars retain a memory of their common origin. They share the same age, the same chemical composition, and roughly the same motion through the galaxy. By measuring the velocities and compositions of field stars, astronomers can sometimes identify groups of stars that were once part of the same cluster, even though they are now separated by hundreds of light years. These stellar streams or moving groups are the ghosts of dissolved clusters, their members still recognizable as siblings even though their family reunion is long over. It is a reminder that bonds, once formed, can endure even in the absence of physical proximity. Globular clusters are far more resilient, but they too are not immune to dissolution. The primary mechanism is evaporation through two-body relaxation and three-body encounters. Over billions of years, stars in the cluster exchange energy through gravitational interactions. Some stars gain energy and are ejected from the cluster at high velocity. Others lose energy and sink toward the core. The cluster loses mass gradually, becoming less gravitationally bound. Eventually, after tens or even hundreds of billions of years, even the most massive globular clusters will have evaporated completely, their stars scattered across the galactic halo. It is a slow process, but it is inexorable. Some globular clusters face a more violent fate. If a cluster passes too close to the galactic center or through the densest part of the galactic disk, tidal forces can become strong enough to rip the cluster apart in a single passage. This tidal disruption creates spectacular stellar streams that trace the cluster's orbit through the galaxy. Astronomers have discovered several such streams, long arcs of stars stretching across the sky, the remains of clusters that came too close to danger. These streams are both beautiful and scientifically valuable, allowing astronomers to map the gravitational potential of the galaxy and understand the dynamics of cluster dissolution. When a star is ejected from a cluster, it does not disappear. It continues to orbit the galaxy on its own, a wanderer carrying with it the chemical signature of its birth cluster. If that star has planets, those planets are carried along as well, their inhabitants, if any, forever separated from their stellar cousins. Imagine being on such a world, knowing that once, billions of years ago, your star was part of a great cluster surrounded by siblings, but now it drifts alone through the galaxy. The night sky would be no different from what we see on Earth, sparse and dark, but the knowledge of that lost community might inspire a sense of cosmic loneliness, or perhaps a determination to reconnect. In the end, the dissolution of clusters is not an ending, but a transformation. The stars do not cease to exist. They continue their journeys through the galaxy, carrying with them the elements they created and the history they experienced. The atoms forged in those stars will eventually be incorporated into new generations of stars and planets, continuing the cycle of birth, death, and rebirth that defines the cosmos. Clusters are temporary, but their legacy is eternal. The universe remembers its children even after they have gone their separate ways. And we, looking up at the night sky, can honor that memory by seeking to understand these stellar families while they last. As we come to the end of our journey through the realm of star clusters, let us turn our gaze inward and consider our own place in this cosmic story. Our Sun is not part of any cluster. It is a solitary wanderer in the galactic disk, separated from its nearest neighbors by over 4 light-years. But it was not always so. Like most stars, our Sun was almost certainly born in a cluster, likely an open cluster containing hundreds or thousands of stars. In the early days of our solar system, we were part of a stellar family, surrounded by siblings that illuminated our night sky with their collective light. Over hundreds of millions of years, that birth cluster dissolved, its members scattered across the Orion arm of the Milky Way. Today, the Sun's siblings are spread across hundreds of light-years, indistinguishable from other field stars except by their shared chemistry and age. Astronomers have searched for the Sun's lost siblings using spectroscopy and kinematics to identify candidates. A few stars have been proposed as possible siblings, but none has been confirmed with certainty. Our family is lost to time, its members wandering the galaxy on their own paths. In a sense, we are orphans, alone in the cosmic dark. Yet this solitude has its advantages. Had the Sun remained in a dense cluster, the gravitational interactions with neighboring stars might have disrupted the outer solar system, ejecting comets and planets into interstellar space or sending them careening toward the inner planets. The stable, quiet environment we enjoy today might not have been possible in a crowded cluster. Our isolation has allowed life to develop without interference, to evolve slowly over billions of years, ultimately giving rise to intelligence and civilization. Perhaps solitude was necessary for our existence. Perhaps only orphan stars can harbor complex life. Our fascination with star clusters is, in a sense, a longing for that lost family. When we turn our telescopes toward the Pleiades or Omega Centauri, we are not just observing distant stellar systems. We are seeing what our own birth cluster might have looked like, a community of stars bound together by gravity and history. We are imagining what it would be like to have neighbors close enough to visit, to communicate with, to share the cosmos with. The dream of interstellar travel, of establishing colonies around other stars, is perhaps a dream of rebuilding that lost stellar family, of creating a new community among the stars. There is something deeply moving about the idea of stellar families. In a universe so vast and so empty, where the distances between stars are measured in light-years and the timescales of cosmic processes in billions of years, the existence of clusters reminds us that connection is possible. Stars can be born together, can share space and light, can influence each other's fates. Even when those families dissolve, the memory remains, encoded in the star's chemistry and motion. It is a poignant metaphor for any family, any community, any gathering of individuals who share a common origin and a common journey, even if they eventually go their separate ways. As we develop the capability to explore beyond our solar system, star clusters may become important destinations. Open clusters, with their relatively close-packed stars and young ages, could be ideal targets for interstellar missions. A single journey to a nearby open cluster could give us access to hundreds of stars, each with its own planets and possibilities. Globular clusters, with their ancient stars and extreme environments, would be more challenging but even more rewarding, offering insights into stellar evolution, compact objects, and perhaps even civilizations that have existed for billions of years. The clusters are waiting, invitations to explore and understand. In the end, star clusters teach us about both connection and impermanence. They show us that even in the vastness of space, families can form and endure for a time. They remind us that all structures, no matter how stable they seem, are temporary on cosmic timescales. But they also show us that legacy endures, that the memory of connection persists even after the physical bonds are broken. As we look up at the clusters scattered across our night sky, we are seeing not just distant collections of stars, but reflections of our own story, our own longing for community, and our own place in the grand cosmic family. We are all children of the stars, and the stars are our eternal kin. Our journey through the stellar families of the universe has come to an end. We have explored the young and scattered open clusters, nurseries of newborn stars that will eventually drift apart. We have ventured into the ancient and dense globular clusters, cosmic cities that have endured for billions of years. We have seen how stars are born together, how they influence each other, and how they eventually go their separate ways, carrying with them the memory of their shared origin. As you drift off to sleep or return to your day, remember that you too are part of a cosmic family. The atoms in your body were forged in stars like those we have visited tonight. You are made of stardust, a child of the cosmos, connected to the universe in ways both profound and beautiful. Thank you for joining me on this journey. Until we meet again among the stars, may you find peace in the knowledge that we are all part of something vast, ancient, and infinitely wondrous.